Good morning. This is going to be an awesome day. We're moving on to section 5.4, Fundamental Theorem of Calculus. This lesson will seem very familiar to you. It'll seem like, hey, didn't we do this last week? And that's okay. Enjoy it while it lasts. What I have written right here is the Fundamental Theorem of Calculus, which you do have in your notes from last week. The integral from a to b of a function is its antiderivative with the b plugged in minus the antiderivative with the a plugged in. Big deal. All right, and I mean that sincerely, it is a big deal. We've been working on that, and that's what we took the quiz on. Let's take a look at a couple examples. The directions will just say evaluate this definite integral. Why is there word definite? What does that mean? Definite is when you have an a and a b here on top of your integral. We will soon do integrals that don't have the a and the b, and those are called indefinite. We'll see how to handle those differently. So first example is number 3 on page 286. Integral from 0 to 1 of x squared plus the square root of x. Let's go through this together. I hope someone noticed I left my dx off, so I'm going to write it on there. All right, so this is the same as the integral from 0 to 1 of x squared plus x to the 1/2 dx. Let's evaluate by taking the antiderivative. Antiderivative of x squared is x cubed over 3. When up a power divided by that number, same thing with the fraction power. I'm going to go up a power, and when I divide by 3/2, that's the same as multiplying by 2/3. Now I'm going from 0 to 1, so I end up having 1/3 plus 2/3 minus 0 plus 0. So my answer is 3/3 or 1. All right, that one probably seems pretty easy after the ones we were doing last week, right? Next problem is number 8 on page 286. Integral from 0 to pi of 1 plus cosine x dx, a trig one. You guys had probably figured out you got to be really careful with those trig functions and the signs, your plus and minuses. Whenever you take the antiderivative, just before you evaluate and plug the numbers in, check your antiderivative. Take its derivative, and it should be the integrand, the part that's sitting there. Okay, antiderivative of 1 is x. Antiderivative of cosine is sine. Let's check it real quick. Derivative of x is 1. Derivative of sine is cosine. Looks good. We're going from 0 to pi. Now we have pi plus sine of pi minus 0 plus sine of 0. What is sine of pi? I didn't hear you. What is sine of pi? 0, that's right, and sine of 0 is 0. So we just have pi here. Okay, those should seem pretty straightforward. Yeah, some of your problems will be this easy. Remember how we can do this on our calculator also. I'm going to take the number 8 example and check it on the graphing calculator. Here, if I do math 9, that pulls up the integral for me, and I'm going to go from 0 to pi of 1 plus cosine x dx, and hopefully I'll get about 3.14. Excellent. All right, so I feel good. This answer's right. Let's see what else we have today. Here's the steps, depending on the directions. We talked a lot, I think, on our block day and on Tuesday about the difference between evaluate the integral and find the area. If the problem asks you for the total area, or area under the curve, or between the curve and the x-axis, you have to separate each section. So the first step is to figure out what the zeros of the function are. You're using this to section or partition off your integrals. Then integrate the partitions separately. And what I wrote for step 3 is either use absolute values of those answers or subtract the negative values so that all of the values are positive, and then add them together and you've got total area. So that's just some nice steps written out. I am going to show you number 4, how to use a calculator to do areas as well. Some of your next test will be calculator, and some of it will be no calculator. So if I look at number 17 on page 286, take a look at that. You notice how it says, it just gives you a function, and it says to find the total area of the region between the curve and the x-axis. So some of this function might be above the curve and some of it might be below. If so, we're going to have to split it up. First step we're going to do is find the zeros. So let's factor this. If I take out an x, I'll have x squared minus 3x plus 2. I can keep factoring. That becomes x minus 2, x minus 1. All of the zeros then are 0, 1, and 2. This is a cube, so it's apparently going to look a little like this, okay? You notice how within our domain 0 to 2, all of these answers are here. I'm going to have to integrate these parts separately. I'm going to have to integrate from 0 to 1 of this function. Then I'm going to have to, since this area is below the x-axis, I'm going to subtract the integral from 1 to 2. Let's say you didn't know, because you didn't know what the curve looks like. We know about x cubed, but if you didn't know whether or not it was above or below, just integrate each separate section separately. If you get a negative answer, you're going to know, oh, that part was below the x-axis. So make it positive if it's asking you for area. All right, I'm going to finish this up. Now, this problem would take a little bit to do by hand. Let's take a look at our antiderivatives here, and I may have to get a little more room. I'm going to go up here for the antiderivatives. The antiderivatives would be x cubed, excuse me. The antiderivatives would be x to the 4th over 4 minus, what's that, a square, x cubed plus x squared. That's my antiderivative. And here I'd go from 0 to 1, and then over here I'd take the same antiderivative and go from 1 to 2. Evaluate both of those and add those areas together. I'm going to leave that there because I think we've had plenty of practice with these. We could finish this up if we wanted to, couldn't we, class? If I wanted to use my calculator, what I could do is use absolute value. You see on step 3, we talked about subtracting a negative, which is going to ultimately make it positive. Doesn't absolute value make everything positive? You may recall when I've graphed these on the board that absolute value takes any part of the graph that's below the x-axis and reflects it up above the y-axis, or x-axis, so you can kind of think about what that would look like. It would take this part right here. Instead of doing that, it's now going to be up here. This part right here, instead of doing this, would be here. In that case, everything is above the x-axis, so we could add those together. How we enter that on our calculator is like this. Note where the absolute value is. It's very important to put it in the right place. The absolute value is around the integrand. It's not outside of the integral. It's inside of the integral. So to enter this in your calculator, you're going to enter it just like that. We're going to do Math 9. We're going from 0 to 2. And now I'm going to put absolute value here. That's math. Arrow over to number, absolute value, and enter the function. dx. Whoops, I put an extra one in. Oh, look at Miss Newland. She's messing up. Delete. I'm just going to clear that out. Try it again. You guys are probably ahead of me because I did a typo. Here we go again. X cubed minus 3x squared plus 2x. And of course, we didn't work this whole problem all the way through to get the final answer. But if we had, we would have realized, struggle. Oh, I see what I did. X. Don't you wish you were here to yell at me and tell me what I'm doing wrong? See how lost I am without you? and it calculates and we get 1/2, which if we would have done it by hand, that's exactly what happened. That one little area was 1/4 and the other little area was -1/4, so we added them together and got 1/2. That's handy, isn't it, to use your graphing calculator? The thing is, you need to know how to do it both ways. Make sure your absolute value is not outside of your integral, it's inside. It comes after you enter your integral. And if you do it by hand, you have to split it up, okay? You're going to be asked to do it both ways. Oops, where did my cursor go? There it is, way up there. It's invisible for me right now. Oh, Miss O'Neill. Hang with me, hang tight with me. My screen's doing weird. Oh, there we go, it showed up. Wonderful. Sigh. Okay, so if you guys would try number 18 on page 286, I want you to do it all by hand, and then I want you to do it on your graphing calculator and check yourself. I'm going to give you a few minutes.
I have that at the desk. We both have one.
Help each other out. To set this up, you should have the integral from -2 to 0 of x cubed minus 4x minus the integral from 0 to 2 of x cubed minus 4x. Those are your two partitions, -2 to 0, 0 to 2. And when you integrate, your antiderivative is 1/4 x to the 4th minus 2x squared. And your answer should be 8. If you need more time, you can pause the video, you can finish it up later. That's okay. Make sure you go to your group partners if you need some help. Last problem that we're going to take a look at is different. It's problem number 54 on the in the book, and it's a graph question. And we're going back to those ones: is the particle speeding up or slowing down? Is the velocity? What's the velocity? Those kind of questions. So remember your t-chart. I'm going to draw it up here because it's been a little while since we've used it. We have F prime, F double prime, increasing, decreasing, max min, concave up, concave down, inflection point. This goes plus, minus, 0, or does not exist, increasing, decreasing, max min, plus, minus, 0. This F is your position. Oops. This F is your position. This is your position graph, your original. This F is your velocity graph. And then this is your acceleration. The directions might look a little different. In the past, they've flat out told you, hey, this is position graph. Hey, this is velocity graph. Yoo-hoo, you're looking at this graph. Now they're going to word it a little bit different. I want to show you what I'm talking about here. If S equals the integral from 0 to something of some function, and they give you the graph of the function, we want to figure out if we're looking at the original or the derivative. So let's take a look at this again. They've given us the graph of f of x. The equation says position equals the integral of the graph that they gave you. The easiest way I have to make sense of this is to show you this right here. If I have s equals the integral of f, and I'm trying to figure out on here, where the heck is f, where's s, which one is which? I'm going to do something with you. If I take the derivative of this side and the derivative of this side, I know we haven't talked about taking the derivative of an integral. We will. It's going to be another theorem, a big deal for us. But just think about it logically. Wouldn't the derivative of the antiderivative, those two would just cancel out because you're undoing what you just did? So the derivative of s is s prime, and the derivative of the antiderivative is just f. So what is the relationship here? S prime is f. F is s prime. So as far as where to put these, s prime is here, which is f. That means s is here. And we could call this s double prime, or we could call it f prime. Now take a look at problem 54. Right above 54, it says, in this exercise, f is differentiable function. The position is s. S is the position, and f is the antiderivative of s. If you look down at 54's graph, right above that hump where the graph is, what are we looking at the graph of? F of x. We're looking at the graph of f. So based on what we talked about, we're looking at velocity. You've probably figured out from tests and the questions in the book, most of the time they give you velocity graph, most of the time. Not all of the time, but most of it. So please have your book open to this graph because I don't have it drawn up on the board. Let's look at question A. What is the particle's velocity at time t equal 5? Which graph are we looking at? Which graph are we looking at? We're looking at velocity. So what is the velocity at 5? We have the point 5, 2 on the graph. So when the velocity is, when x is 5, y is 2, or more appropriately when t is 5, although they have x's and y's. So part A, what is the particle's velocity at time t equals 5? 2. Is the acceleration of the particle at that time positive or negative? The relationship between that graph and acceleration is its derivative. So is the derivative or the slope at 5 positive or negative? You got it, negative. C, what is the particle's position at time t equal 3? This is new for us. We haven't done a question like this. If you're looking at this graph, and I'm going to just very sloppily draw it up for us. It looks a little bit like this. It wants to know the position at time t equal 3, but we're given velocity. To go from velocity to position, what do we have to do? Take the antiderivative, correct? Because we're going this way. We don't have a function to take the antiderivative of. There's no function to go up a power and divide. There's no trick. We don't know what this function is, but we do have a graph. What is the relationship between a graph and the antiderivative? Area under the curve is the integral, correct? So if we want to find the position at time t equal 3, we want to do the antiderivative or the area, because they're the same, remember, at time t equals 3. Can we find the area from 0 to 3? We sure can. It's a triangle, isn't it? And that triangle right there is 1/2 base, which is 3, times height, which is 3, so 9/2. Apparently, its position is 4.5. That makes sense. How the question asked us for position, we were given the derivative or the velocity, so we had to do the antiderivative, which is represented by area under the curve. All right, the next question. At what time during the first 9 seconds does S have its largest value? Let's talk about what it's doing. At this point right here, where we're walking, what are we doing? We're walking forward. Are we still walking forward? Are we still walking forward? Yes, we're slowing down, but we're still walking forward. We walked forward until we got right here. And now what's happening is we're actually walking backwards, aren't we? So from there. So at what point was what is the particle at its, which is S, S is its position, at what point is its position have its largest value? It's going to have its largest value right there at 6, because at 6, it started getting smaller. This area is growing, 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 growing. And now, because this area is smaller, our integral would actually be becoming smaller at that point because it's below the x-axis. Flip the page over. Next question. Approximately when is the acceleration 0? Remember that acceleration is the derivative or the slope. So it looks like it happens 2 times, doesn't it? I'd say right about 4-ish seconds when it got to that first hump, and then right about again right around 7 seconds. F. When is the particle moving toward the origin and away from the origin? Now on this problem we are starting at the origin. For a while we're always going to do that, and I don't want to talk necessarily right now about how you can tell. So this is starting at the origin, and we've already talked about at this point right here, if we're at the origin, we're walking away from the origin right now, okay, because we're walking forward, forward, forward. At this point, at 6 seconds, when we turn around and start going back, we're walking toward the origin again. So we're walking, because we're walking backwards from where we were. So we're walking forward from 0 to 6 seconds, or away from the origin. And then from 6 to, what is it, 9 seconds, we're walking toward the origin. On which side of the origin, G, on which side of the origin does the particle lie at time t equal 9? How far did we walk forward? You can't exactly tell, can you? I can't tell, but I know we walked forward all of whatever this area is. We were walking forward all that time. We already know that it's bigger than 4.5 because we kept walking forward and forward. And then we started walking backwards. We walked backwards this far, where I colored in the red. So based on what I colored in, do you think there's more black or do you think there's more red? Yeah, we walked forward more than we walked backwards because that area is clearly larger than the negative area. So that means that the answer to this question is it's going to be on the right side of the origin. Are they using right and left, or are they using forward? I think they're using, well, we could just say on the right of the origin. So we're just another velocity graph question. I kind of like those. They're fun. I know you think they're fun. You just don't want to admit it because you're a nerd. All right, so there's your assignment. You have 5, 4, 286. There you go. We're going to do every third problem. So like 1, 4, and go from there. 7. Do every third, and then we have a couple more. Please help each other out, and I will see you tomorrow.